Hello and a warm welcome from Physics for Students. A very good evening. And today marks the 146th birthday of Albert Einstein. And on this occasion, from Physics for Students and from my side, Shaunak, I would be presenting today a complete overview in understanding Einstein's general theory of relativity. Now, today is also a Pi Day, but most importantly, that it marks 156th birthday of Albert Einstein. I hope my audio and my video is clear. Yes, thank you, Priya, and wishing you a happy Holi. I hope my audio and video part is clear, so I can straight away go ahead because there are a lot of things that we need to present today. So let us wish this extraordinary talent, Albert Einstein's happy birthday on his today is the 146th birthday. So we will start today's understanding of general relativity in understanding what is called a general relativity and what is a space-time curvature. Now, I would request all the viewers that some of the concepts of general theory of relativity, what I will be talking today, might sound a little bit mathematical, might sound a little bit difficult, but just hold on. By the end of today's session, you will be able to understand everything. Happy Holi, Harshad. Warm welcome to today's session. Now, what we see in terms of general theory of relativity is that it is a theory of gravity, which was published by Einstein and others, because there were collaborators who were responsible for this. And it was published in 1915. Now, as you can see right on the screen, that there are certain, yes, Raghav, wishing you a very happy Holi. So as you can see, the straight lines, which were thought as straight lines on Isaac Newton's time, were turned to what are called geodesics. Don't worry, we will cover what are geodesics today. And this in turn turned into black holes and neutron star and those which have got a very deep space-time curvature. Also, the straight line, and as you can see, are now converging to a point, which is what are called geodesics. And this led to what are called Einstein field equations. Don't worry, if you don't understand, we are also going to cover that. And space and time, which was thought to be two different axes or two different coordinates, were unified as a space-time continuum or something which is a single identity by Albert Einstein. And this led to a lot of tensors. Please do the next podcast with Professor Jayant Vishnu Narlikar. I don't have reach to this great person, Raghav. I mean to say, I will try to contact. You have told me earlier also, but I will try to do that. And this actually contains a lot of tensor equations, which sometimes make the Einstein field equations look a little bit complicated. But we will try to make things easy today, because the best celebration and telling Einstein happy birthday is to understand his general theory of relativity. So from this part of the video, we can understand that these are something which were extended to different parts of general relativity. Now, the original thought of general theory of relativity actually start with this one, which is called the Entwurf document. Now, this is basically a German word which I won't dare to pronounce. As you can see, the left-hand side is his friend Marcel Grossmann, and on the right-hand side is Albert Einstein. And this was actually a collaborative effort which was done with Einstein and Grossmann, and which actually started around 1912 and 1913. I have mentioned in my videos earlier, which is called History of General Relativity, and it finally led to 1915, the foundation of general theory of relativity. So this is actually the original paper. Now, here you can see the Entwurf equations. Entwurf in German actually means draft. Okay, just a question to all of you who are watching. Is my video and audio and the light and everything is clear? Because I put on a different kind of a light. Can you hear me clearly? Can Raghav or Priya, Priyo just put up a yes and no in the comment box? Is my audio absolutely clear? Please do let me know. So the 1913 Entwurf, or the draft that Einstein and Grossmann actually did, is something which actually showed that there was some kind of a problem. And the equation, yes, all things are clear. Oh, great. Thank you, Harshad. So there was a problem, and this problem, I won't describe this problem right now. If you go to my history of general relativity 3 equations, there you will find that the covariant theory of gravity or the tensor equations were not being able to found out. I mean to say, Einstein was not being able to find out what are called the tensor equation. So that was basically the problem of the collaborative effort of Einstein and Grossmann. Thank you, Priyo. Now, this is actually, during that time, it was called Prussian Academy. Now it is after the Second World War, everything has changed. This is actually the original paper, which is called Reports of the Royal Prussian Academy of Sciences, Einstein Field Equations of Gravity, which was published in page number 844, and it came out on Berlin in 1915. Okay, yeah, good night, Raghav. So you won't be there in today's podcast. Okay, fine. So this is actually the original paper which was published. Now, this paper actually gave us a lot of things. First of all, as you can see, that the perihelion precision of Mercury, I think most of you know that there was a problem in terms of calculating Mercury's perihelion, which was done by Isaac Newton, but later it was corrected by Albert Einstein. So it was 43 arc seconds per century, which is actually a lot of amount. So that was not matching with Newton's equation. So this paper corrected that. And on the 29th of May 1919, when Arthur Eddington actually did what is called the eclipse, solar eclipse experiment, it found that the starlight is little bit bending. And why it is bending? Because the sun has come near, and as sun has got a mass, so it is causing the space-time to curve. And this is actually called the gravitational time dilation. So the light is not bending, but it is appearing to be bent because the curvature is there, the star is there, the light is there, but it appears to be bending. So this was very important because this is the first time that Einstein's theory of relativity was proved on observational effect, that somebody actually observed that yes, space-time do curve. Now, if you look at in Google or you search out anything related to general relativity, you will always find these 3 pictures most commonly. Okay, so what these pictures tell is that there is a mass, or there is a kind of a surface, and there is a heavy ball on the surface, and this heavy ball is actually causing a kind of a dent. That means there is a think of a bed sheet, and you put a heavy mass on it, the bed sheet will curve. So from these equations, what it tells is that general theory of relativity is all related to space-time, curvature, mass, etc. Now try to imagine one thing: when you go to Google and when you search out anything related to physics, so can we publish a paper at the age of 18? I will meet, please get in touch with me later. I can definitely help you out with this. Right at this moment, we are talking of an agenda of general relativity. You can just contact me over my WhatsApp and email. I will tell you what are the procedures of publishing. Now, when we talk of classical mechanics or classical relativity, you see what happens generally is that we get a kind of a pendulum. There is a pendulum which is going to and fro. So that means it is something related to pendulum or classical physics. But whenever we see this kind of a picture, it actually shows that there is a change in the physics, that there is a mass and there is a body, etc. You go to internet, and if you type out these words, for example, what is general relativity, then you will see in Wikipedia or Britannica, etc., all of these papers actually tells that it is Einstein's theory of relativity, it has got curvature, etc. So that means we can tell that it is basically general relativity is the study on the curvature of space-time, which is caused by the presence of mass and energy. So there is a mass which is present, and just placing a heavy ball on a bedsheet creates a curvature. So it also creates a curvature. This part of the, I think this is all going nice and fine. Please do let me know in a comment box. I would like to interact also. So this part of the of our today's session actually tells the origin, the original paper, how Marcel, Grossmann and Einstein finally found out what is called general relativity, and it is basically it is a study of curvature and space caused by mass and energy. Now, when we come to the next part of our understanding, that is what is called special relativity and general relativity. Now, here is a note I would like to, tell all the viewers. Some of the people who are new, who are young people, you might think that special relativity and general relativity are two different theories. But the fact is that, okay, my contact number, I can give it here. Okay. Okay, so special relativity and general relativity, they are not two distinct theories, but actually special relativity, general relativity came out of special theory of relativity, is actually an extension. It is actually, I would say, a generalization of special relativity in general relativity. So in this part of our understanding, we will look in some of the very important results and how from special relativity we went in general relativity. Just a quick questions. Are you enjoying today's session? Just let me know in a yes or no. I really would like to know, or it is getting a little bit too boring or technical. Just let me know. Okay. Now, here you see that special relativity and general relativity, as I have written, these are not two independent theories. Special relativity is based on inertial frame of reference. And what do we mean by inertial frame of reference? That means things where there is no acceleration. Okay, things which have got no acceleration. So a frame is moving at a constant velocity. Okay, there is no fictitious or any pseudo force. The Newton's laws of motion, F equals to ma, etc., holds perfectly well. For example, a reflection on the signs of gods. Yeah, hello. And most importantly, you can imagine that a spaceship is moving in deep space, something like that. Now, when I say F equals to ma or Newton's laws of motion typically holds in special relativity, there is a problem. I mean to say, this won't be very accurate to tell that Newton's law hold accurately in special relativity. It doesn't. Now, let me show you what is the problem. Now, here you see Newton's laws were actually formulated based on classical physics. And classical physics assume there is an absolute time. You understand what is an absolute time? I mean to say, there is the time is just going tick, tick, tick. That's all. There is an absolute space. That means space is common for everybody. And there is something which is called a Galilean relativity. And what do we mean by Galilean relativity? So if you are on a moving train and the train is moving at 10 kilometers per hour, you are moving on the train 20 kilometers per hour, then 20 plus 10 equals to 30 kilometers per hour. That is what is called Galilean relativity, where the velocities just add up. But as we will see in special relativity, it never happens. Because if you add the speed of light with your velocity, then you get something which is more than the speed of light. And that is not possible. So here is a problem with Newtonian mechanics when we apply to special relativity. So here you see that in special relativity, these things modifies, yes, but very important, it does not invalidate Newton's law in the domain of applicability. What we see is that they often say, sir, Einstein proved Newton wrong, or Newton proved Galileo wrong. No, nobody proved anybody wrong. Every single person is correct. Every single person is right. Only that Newton's laws of motion had got limitations in a certain velocity, in a certain frame. And Einstein improved that. So please note this line, that special relativity does not invalidate anything, but it actually modifies the laws of motion. So if you say of the compatibility, absolutely, very true. I don't know your name, so if you can put it over, that would be great. So, so Newton's first law of motion, a body in rest will stay at rest until it is moved by a force. So everything stands true, right? But it has to be in an inertial frame of reference. That means there is no acceleration, there is no speed which is there. So here I have written at the bottom of the line, relativity only modifies how we measure motion at high speeds. But the fundamental principles are very much valid. So this is a note that we should remember. Now you see from here, when we move in this part of the of our understanding, Now F equals to ma. This is where mass is constant. Now, you know, in special theory of relativity, mass is not constant, but as we move with the close to the speed of light, mass changes. So I have given a very simple calculus derivation. From F equal to ma, we can write it as m dv by dt, which is equals to ma. That means in classical physics, we can tell that the force is the rate of change of momentum, and this reduces to F equals to ma. Very good, very true. You will agree to me. But here you see what happens in special relativity. F equals to same ma I am substituting by d by dt, but here we get a gamma mv. Okay, this mv is basically mass times velocity, which is the momentum. But we have a factor which is called gamma. And this gamma is basically called the Lorentz factor. If you say that what is Lorentz factor, I'm not covering here, but you can just think that it is a mathematical equation which actually, I would say, which actually shows the equation of motion correctly. If you're moving close to the speed of light, then the Lorentz factor or Lorentz transformation is a mathematical equation which helps you to calculate those velocities. Now here you see that we get P equal to mv, which is a classical momentum, and we get rho, for example, equal to gamma mv. This is basically what is called the relativistic effects. This gamma is actually the relativistic effect. Now here you see, don't worry, we will come to this. In special relativity, we don't have a momentum. We have a 4 momentum. Don't worry, I will cover what is 4 vector and 4 momentum today. So 4 momentum is something which has got a x, y, and z direction, and it has got the speed of light, mc. Okay, and this gamma term is actually multiplying. So mass times velocity in x direction, mass times velocity in y direction, mass times velocity in z direction, and mass times speed of light. Now we will come to this. So special relativity, actually we have got a 4 momentum, and this 4 momentum was not present in Newtonian mechanics. So that is why I told you that we cannot tell strictly that the Newton's laws of motion will apply on special relativity. It needs to be modified, and this modifying factor is the gamma factor. Okay, now here is something which most of the students make a mistake. Now here you can see that this m is the rest mass. But remember, nowadays in modern physics, we don't talk of rest mass. Okay, rest mass or relativistic mass, we don't talk about it. We tell that this is an invariant mass, and it is the same as in all frames of reference, which is commonly called mass. Whenever we talk of mass, we means rest mass or classical mass. Now, some of the relativity old textbooks will write like this: mrel means relativistic mass equals to gamma times m, which is the constant mass. Why only 4? There can be cannot be more or less. No, there cannot be more, because we are dealing with 4-dimensional space-time. Meet Shah. Okay, we are dealing with time and x, y, z. So that is why we have got a 4-dimension space-time. So that is why we have got a 4 vector. Just stay on the on this session. You will understand what is a 4 vector. Okay. So we actually don't tell that we have got a rest mass or a relativistic mass. We tell that as mass as increasing, we describe through what is called momentum and energy. So you see P equals to gamma V is the relativistic momentum, and E equal to gamma mc square, which is the famous Einstein's mc equal to mc square. So that is why we got a relativistic energy. So we say mass does not increase with velocity. We don't tell that, although it happens, but it is wrong to tell. Modern physics tells that momentum and energy behave relativistically. Now I will show you what do I mean by momentum and energy behave relativistically. Here you can see, when we first concentrate on this first part of the slide, m. M is what? This is the mass, rest mass. Okay. Momentum increases with velocity. Why? Because P equals to gamma mv. Okay, not because mass is increasing. It is the gamma factor. So when we are moving close to the speed of light, energy increases with velocity. Okay, so we get E equals to gamma mc square, and this m remains constant. And here you can see this yellow box. It is moving close to the speed of light. That means the total energy remains constant, but here the energy increases with velocity. So here the gamma increases, increases, and increases. And how it increases, if we put that square root of 1 minus v square by c square, which is the Lorentz factor, you get this value. Now see at the bottom, if you're moving 10% close to the speed of light, the gamma is only 1.005. That means there is got no effect. Now you move 90% to the speed of light, the gamma is 2.3, much bigger. And even if you move 99.99999% to the speed of light, the gamma factor is 70.7. That means it increases very high. Now here is a misconception. I would like to give you an example. Now say for example, when we were young, when we were in school days, going from Calcutta to Delhi or Delhi to Bangalore or something, it would take, for example, 2 days over train. Okay, I'm just giving you an example. It would take 2 days from Calcutta to Delhi, or one night journey. Okay, now with this Duranta and other trains coming up, say for example, we reach Delhi from Calcutta to Delhi within 4 hours time. That means what? Speed has increased. But does that mean that a person's clock in Delhi will run slower and my clock on the train will run faster? I mean to say, time dilation will happen. The answer is a big no. If I travel via train from, for example, from India to say, for example, Mauritius, for example, weird example, and it takes 10 days or 3 days for me to travel from India to Mauritius, and by a super fast train or a jet plane, if I go from India to Mauritius within 3 days, does that mean that the person's clock in Mauritius will record a different time and my clock will record a different time? No. It will measure the same time. Now, what does that mean? That means speed compared to this part, I mean to say 1 day or 2 days or 3 hours or maybe 2 hours, actually does not make any sense. Only when you're traveling close to the speed of light, then only the time dilation will happen. I will show you a practical example today. What do I mean by time dilation? So in general practice, in day-to-day experience, for example, you are there in Bangalore, I am there in Calcutta, you are moving fast on a train or on an auto or something, and I am moving slowly. Do you think our clocks will mismatch? No. There will be absolutely negligible. There will be no effect. And the reason is this one, right at the bottom. Only and only when you're traveling close to the speed of light, these changes happen. So we can say that instead of saying mass increases with velocity, we say that momentum and energy behave close or relativistically while mass remains invariant. Are you all enjoying today's session? I mean to say, can you just put up a yes, no? Because I always, sir, how we came up with the gamma factor being a multiple factor and why not, why logarithmic or exponential factor? Meet. This is something very trivial, which is called a Lorentz factor. I can show you through example. I need to have a whiteboard and I need to show you. But this is out of the scope of today's, because I have to cover a lot of topics today. Okay, so just go and find out the derivation of Lorentz factor. You will understand. I think you need to go a little bit in the basics of special relativity. Don't take me wrong. I can also teach you. But this is why not logarithmic or exponential factor. It comes out of Pythagoras' derivation. Okay, so just go and get in the basic understanding, you will understand. Okay, so I was just asking that if you can put up a comment in the comment box that whether you are enjoying or things are going fine or is it too fast or not. Okay, so here you see when we say that speed increases or the Lorentz factor happens, here you can see anything which has got a non-zero rest mass. I mean to say any, okay, enjoying very much. Any others? Oh, Dr. Azizur Rahman. Hello, sir. How are you? You are also enjoying. Great. So when you have got a non-zero rest mass means which has got a value. I mean to say it is not zero. It can never approach the speed of light. Because it has got a mass, it can never approach the speed of light. Why? I will show you right now. The energy, the green one, energy approaches infinity as velocity approaches close to the speed of light. So we need a huge amount of energy to push a thing which approaches to the speed of light. Now here you can see Meet, I was just, you were asking me this question, why not exponential? Now you see here, we get special relativity momentum is what? Same, Newtonian mechanics, P equals to mv, we put a gamma factor. This is the Lorentz factor because of the speed of light. Now what happens when the velocity of an object, for example, I am moving close to the speed of light. So if I substitute the gamma 1 upon v square by c square and put it on this P equals to gamma mv, you can see what happens mathematically. Here you see. So I put P equals to mv upon 1 upon v square c square. That means what I have done from this equation, I have just substituted gamma. So gamma 1 upon v square by c square times m times v. Now as v approaches c, what we get? We substitute the value, that is instead of v, we write c. Now you see what happens. P equals to mv 1 upon c square by c square. C square get cancelled off. And what we get? 1 minus 1. Square root of 1 minus 1. That is 1 minus 1 is 0. Square root of 0. Anything upon 0. What is that? That means it is undefined. It blows up to infinity. So Meet, you got the answer to your question. As momentum approaches infinity, the velocity of a body also approaches close to the speed of light. So we can say an object with mass, any mass, cannot reach the speed of light because you see the entire equation blows up and the momentum would become infinite, requiring infinite force to accelerate. So this part of our video or this part of our understanding actually tells from special relativity how we move to the close to the speed of light and what are the changes that happens with Newtonian mechanics when we just do the same thing, the same momentum, same velocity, but we are just substituting the Lorentz factor because here we are not moving as a car or a bus or an auto, we are moving close to the speed of light. So here the equation blows up. Okay. So this is what tells that why special relativity and general theory of relativity are actually not two different things, but they actually being generalized from Newtonian mechanics to special relativity and so on. Now we come to what is called the next part of our understanding. That is a very important part, which actually takes us to general relativity, which is called space-time and space-time. That means in Newtonian mechanics, space and time was different, and here now it is unified. Now, what are the changes actually happen? Now, just try to imagine that something, for example, if I take a box, now let me give you a simple example. If I take a box, something like this, and if I take a mobile, something like this, then I can explain this box is a box. If I open, there is my pen drive, there is my eyedrop, and certain other things. Okay. Now, here is my mobile, which is over there. So if I tap my mobile, I will see certain notifications and I will go ahead and learn. Now imagine that this box and this mobile are now one single unit, united, something like this. So you don't call it as a box or a mobile. You call it, for example, Bo-mobile. Bo-mobile, that means a box and a mobile. That means if I change something in this mobile, this box is also going to change. And if I change something in this box, this mobile is also going to change. So box and mobile are not two different identities, but now they are unified as one single identity, which is something like that. This is exactly which happened with this part of our understanding. Now here you see when space and time was different, space and time were two coordinates. Okay, before Einstein, they were separate entities. So space moving here, time moving here, etc. Now, what happened is that this red one, this dot, actually, Einstein told there are certain reasons, which is very deep with Maxwell's equations. I'm not telling it right now, that space and time will be now united in one, what is called a space-time continuum. Now, the moment space and time is united in one, the famous Pythagoras' theorem, hypotenuse square equal to base square plus perpendicular square, this actually takes a different shape. And this is called the same one, ds square equals to minus c square dt square plus x square plus y square and z square. This dx and dy are infinitesimal small distances. Okay. Just hold on for a second. I would like to open the paint brush, and I will just like to show you something. If possible, I can just share the screen, which will make things better. Okay, share screen. Okay. Okay, now can you see my screen? Okay. Now here you see, for example, if, let me take my brush, yeah. So for example, when this space in this direction and time was in this direction, for example, these are the two directions which we have. Now, once we put it in a kind of a continuum, something like this, then what we need to do is that, for example, if I try to find out something for this particular region, and something for this particular region, and something for this particular region, then what I need to do is that I need to apply the rules of calculus. And I need to, break these things up. For example, I can, let me use a different, I can break this thing up. I can break this thing up. I can break this thing up into small different parts. Okay, small different parts. And this is what is called the differential or the infinitesimal volume. So it can be dx for the x direction. It can be dy for the y direction, and so on. So these are basically small, short distances which we want to measure, because now we cannot measure in this and this direction, but this is a space-time continuum. So all is taken up in one small pieces, and this is what the dx center. So dx squared means the same hypotenuse squared, but now we are measuring all the infinitesimal distance in this x direction, all the infinitesimal direction in y direction, and all the infinitesimal distances in the z direction. So this is dz. So that is why we are applying calculus, and we are actually finding out these small distances. Okay, so this is just to give you an idea. Now, if you look in this part, you will see that this might sound a little bit complicated. Further, this space-time interval is getting generalized into what we call is a metric tensor. Don't worry, I will cover up this part later. But remember, the bottom line is very important. The concept is generalized to a dynamic metric that depends on space-time coordinate. That means what we can understand till now is that space and time are now united into a kind of a space-time continuum. And in order to measure the infinitesimal small distances, we are changing the Pythagoras' theorem into dx squared plus dy squared plus dz squared. Essentially, the things are the same. Now here you see, space and time are not separate. That means if I change something here, something is going to change. Remember that box and mobile example? If I change something in the box, something is going to happen on the mobile. If I change the mobile, something is going to happen in the box. Okay, so now we come to the very important and a very fascinating part, which is this space-time. Now, because space and time is now united, there are a lot of things which happens. The time dilation, etc., which happens. Now, this effect is happening. This effect would not happen if space and time were two coordinates. Now it is united into a space-time continuum, so that is why it is happening. Now, before I go ahead, I would like to make a quick announcement for the upcoming podcasts. Now, here on the 16th of March, that is day after tomorrow, we have got a podcast on black holes and singularity. But this is not happening on this channel. It will be happening on my other channel. And a very popular person called Astro Kshitij has got an Instagram page also. He will be coming and talking on cosmology and black holes. On the 30th of March, I request everyone not to miss this one. Professor Dr. Madhu Krishna, who is basically a gold medalist. Yes, and she has got 3 gold medals, and she is from the Department of Mathematics of Jadavpur University. She specializes on Roy Choudhury equation, general relativity. So very, very important podcast coming up on this 30th March Sunday, right on this channel. And again on the 20th of April on my other channel, there will be a podcast with Sumana. She is an aerospace engineer on cosmology and orbital mechanics. So I just thought to make you understand that these are the upcoming podcasts which you can. Okay. So now we come back to dilation, gravitational time dilation. Now, In order to measure that gravitational time dilation, I would request you to imagine something like this. Now imagine this is a light clock, okay? And there is a tick tock, 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 a constant motion which is happening up and down. So one tick tock, tick and tock may be 1 second. Another tick tock is another. So constantly there is a light clock, okay, and there's a pulse of light which is going up and down, up and down. I want all of you to imagine that you're holding this light clock in your hand. Okay, let me show you. Okay, now here you see I cannot show you the animation because StreamYard does not support it. So if it is going tick tock, tick tock, tick tock, this is what is called the proper time. Proper times mean the time on your wristwatch. Okay, there are two mirrors. The light is going from here and is going here. It is coming from here and is going here. So this is denoted by delta t or delta t0. Now you see what is called the time dilation. Now imagine this part, that if you are moving, now I want you to imagine this. We'll love to attend. Yeah, thank you, Dr. Azizu. Now say for example, if you take this light clock, okay, tick tock is happening, and you move this one, okay. Say for example, I'm making a slow motion from here, I'm moving to here. So what will happen? This tick tock will not happen like this. It will go tick tick here and then tock over there. And if I move further, then tick and then tock over there. And now you can see this diagram. So here you can see that this tick is happening over here and the tock is happening on a diagonal line. Again, the tick is happening over there and the tock is happening much later. So moving clock from an outsider's point of view, as I told you, your clock is running perfectly well. If you move with the light clock, you will see the tick tock is happening perfectly. But a person who is standing outside will find that the tick happens over there and the tock happens over there. So that is why it is called moving clocks run slowly. And this is what is due to the speed. We will see what is time dilation and gravitational time dilation. But what is important is that this delta t is the proper time. That means the time that you see on the wristwatch, there are no abnormalities. But the person, as you can see at the bottom, who is standing with a microscope or a delta t hash, that is the person who has got a, see, the clocks are running slow. And here you can see if you move faster, then the tick happens over there and the tock happens much later. So that means that the path is longer compared to that of a stationary clock, and the longer path, but the same speed of light. That means the speed of light should not change because that is constant, right? That is special theory of relativity. But as the speed of light is constant, then what is causing that delay? That is because of the time dilation. So if you move faster and faster, the person who is seeing those clocks from outside, they will see that the talk is happening so late that it is coming to be slow. So the light path is not straight, it is diagonal. And slower tick means the time is running slow. And from here, we can understand this now clearly, that if Alice and Bob, Alice is on Earth and Bob is speeding close to the speed of light and very fast in outer space, and you will see that as because the tick is happening over here and the talk will happen much later, Alice on Earth will become much more older because for him the tick tock is happening in the same space. Now here is something, a kind of a confusion, which you might think that how aging happens. That means my hairs will become older. Yes, it will. Because all our body, all our nature, for example, my eyes, my hairs, my body, my gene, they actually decay at a nature's certain rate. Now, if that decay or the nature's certain rate is slow or fast, the changes will happen accordingly, obviously. So Alice, when he is on Earth, his tick-tock is the same as the wristwatch. So the body decay is happening at a normal rate. But Bob, who is moving faster, that means the speed of the light or the movement or the decay of the body is happening much later. The eyes are growing old, the genes are fading much later. And that is why he will come as much younger. And he will see that Alice has grown much older. So this is the famous concept which is called the time dilation, and that is why things become very slow and fast and whatever happens. So remember, it is nothing unscientific. It is very scientific, and this happens because of the speed of the light. All of you, are you being able to understand what I'm saying? Can you just put up a yes as soul strings with Vishal and other? If you can just put up a yes, I will feel happy. Okay. Now, from this time dilation factor, which we see due to the speed of the light, there is another time dilation which takes place, and this is called gravitational time dilation. So the concept is the same. We will take the same tick tock happening over there, but what we see is this one. Now here you see the notation changes a little bit. The dt is the proper time. There was delta t, and the d tau is basically the moving clock time. Now here you see it happens because of the curvature. Because if the space is curved, very much curved, then the tick will happen over there and talk will happen over there. So it is because that instead of motion, we have space-time curvature affecting the photon's path. And this is why it is called our gravitational time dilation. So time dilation is happening over there in the same way, but here you can see the curvature is more. And that is why near black holes, you will see a person who is standing outside the black hole will see that the person is never reaching the black hole, although the person or the astronaut has already reached the black hole. Why? Because, okay, Avinash is saying yes, sir. Thank you, Avinash. So you are enjoying this. Okay, great. So that is why in general relativity and near black holes, things happen much, much slower. Okay, because there is a huge amount of curvature. And you will see, I will tell you that it is not only true. If you put a clock near Earth, near the surface of the Earth, and you put a clock far away space, you will see the clock near the Earth is actually running slow, because Earth has got a gravity, and this is causing the curvature, and that is why the clocks are running slow. And here you can see there are two things which happens. One is a redshift. Redshift happens when a light source moves away and the wavelength of the light stretches. It actually stretches and it becomes red. Okay. And blue shift is the opposite, when a light source moves towards an observer and the length is getting compressed and it shifts towards the blue end of the spectrum. Okay. So same thing, the opposite things are happening. One is getting, stretched, that is the red shift, and another is getting compressed. So stretching happens, that is why the infrared becomes red, and the compressing happens, so it becomes a little bit blue. So that is why it is objects closer due to Doppler effects are seen under strong gravity. And examples, for example, Andromeda galaxy is blue shifted because it is moving towards the Milky Way. So the galaxy is moving towards the Milky Way. So that is why it is called blue shifted. So these things happen, and this is what is called gravitational time dilation. Now, if I see the mathematics, it is more or less the simple one. And here you can see delta t hash. This is the time experience someone closer to the massive object. You can just simply think that it is same as the moving frame in special relativity. And the delta t is basically the time observed by faraway observer. That means who is standing outside the black hole. And m is the mass, g is the gravitational constant, c square is the speed of light. Now, why this r is there? Okay. Now I would like to again share my screen a little bit, because otherwise you won't be able to understand this R. So let me, where is the sharing? Yeah, present, share screen. Okay, here is my screen. All of you can see this one, the screen? Okay, yeah. Okay, now you see, if I again take a kind of a curvature, something like this. Say, for example, if I take a curvature like this, curvature like this. So here what happens is that if I take the vectors, for example, I'm sorry, this is with mouse I'm doing. So if I take this one R, not this one, I would say R, okay? This is the radial vector. So what happens when you see these things are being curved over here? This part of the R, this actually stretches out. If you talk of a rubber sheet geometry, the rubber sheet, here you can see that the R's are already stretching out. So what happens in case of special relativity, we get a vector which has got a straight line. So if this is a vector V, it will be a straight line. But in case of a space-time curvature, these are radial vectors, which will actually, you can see over here what happens. Let me use a different color. Over here, what happens is that, over here, what happens is that the space-time curvature, the R, actually this part of the mesh, it will a little bit stretch. It won't be like this. It will be something like this. It is very difficult to show right now, but it actually stretches. Now, because it stretches, all these R's or the radial vectors also become something like this. It is not the special relativity vector. It becomes like this. Okay. So that is why we are using this R instead of V. This is called the radial vector. So as we move close to the speed of, as we move closer to something which is a gravitating object, it is not necessarily a black hole. This is again a misconception. It can be any gravitating object. You will see that time runs slow. Okay. Now from here, what we get are a few of the misconceptions. Please read this out. Time dilation is not an illusion. We have seen through scientific experiment, for example, through muons, etc., time dilation actually happens. The traveler experiences time slowing down? No, absolutely no. In their own frame of reference, it works absolutely perfect. Gravity slows down time because it physically affects? No, it is just because of the curved space-time. If you remember this part of the slide, yes, that is why gravity slows down. I mean to say this is just because of the curvature. Okay. And gravitational time dilation can be seen near black holes. That is again a wrong concept which I was telling. It is very well seen near any gravitating object. Also, if time slows down, people living there will notice? No, local observers can notice. And people sometimes think only moving clocks run slow. No, in general relativity, even stationary clocks in gravity run slow. So you can read the bottom part that just like velocity induced time dilation in special relativity, here what happens, it is because of the curvature, the time dilation happens. So more or less the concept is the same, but only thing is that it is due to the curvature and that is due to speed and velocity. How are you enjoying? Okay. So we come next to one of the most important part of our video, which is called 4 vectors. Now, I am going to talk about this 4 vector. Why? Because we need to understand something which is called a tensor. I hope those who are maths graduate or who are into physics, you already know what is a tensor. But what you need to also understand, the tensor does not just came because today is 14th of March and I'm feeling very happy, so we invented tensors. It is not like that. What is important is that how tensors actually came and what were the limitations of something which are called 4 vectors. Okay. So now here you see 4 vectors are something, as I told you, Meet Shah was asking that why it was not 3 or 4 or 5 or 6. Now here you can see that because we need to unite space and time in a space-time continuum, so we need a kind of a mathematical entity where all those things, as I told you, that space and time. So if the box and the mobile needs to be united together, we need a mathematical object where space and time is united together. And this is what is called a 4 vector. So ordinary vectors, here you can see ordinary vectors have got something which is called x, y, and z. Ordinary vectors actually do not help in uniting what is called a 4 vector. So that is why in 4 vectors, position, momentum, and velocity, these are not invariant, and 4 vectors is required because in relativity we need to combine time and space. Okay, so this is basically one of the features that 4 vectors actually have. Now here you see this is how actually the 4 vector looks like. You can see there is an x mu component, which is the time component. As I told you, velocity where c is the speed of light. And then you can see x1, x2, and x3. These are the spatial components. Okay. And this is Lorentz invariant. That means that individual components of the 4 vector, just like space and time and coordinates changes, they also change when switching reference frames at different velocities. As I told you, we need to change frames of reference because we are not in a flat space-time. We are in a curved space-time. We are moving close to the speed of velocity. So in case that there is a change in coordinate, these things won't change, right? This is called invariant. Invariant means that doesn't change. So we got the time component and we got the spatial components. So together they make up what is called a 4 vector. Now here you see this is how a 4 vector looks like in case of special relativity. So in special relativity, as you can see, space and time are connected. So Ct is basically the speed of light, which is the conversion factor, and it tells how space and time coordinates transform. And then you can see x, y, and z. These are the spatial components. Now, also you can see this is something which is called the 4 momentum, energy momentum. So as I told you that in special relativity, we do not have a typical Newtonian momentum. We will have a total energy E, and then we have PC, PXC, PXY, and PZC. So these are the what we call the spatial components. So in special relativity, 4 vectors actually live in a flat space-time. In general relativity, later it actually changes this one, ds squared is equal to g mu nu. We will not cover this in today's video. This is called the metric tensor. So understand that 4 vector is a mathematical tool which was required in special relativity because 3 space component and 1 time component needs to be united in one area. So that is why we get something which is called a 4 vector. But 4 vectors also has got a limitation. When special relativity was going on, there were certain problems and limitations of 4 vectors. I will just briefly go through. I won't go much in the details. The first one is because 4 vectors actually, they cannot describe electromagnetic field. So when we talk of electromagnetic fields, which has got an electromagnetic field tensor, they cannot describe it. Also, you will see that 4 vectors cannot describe stress, pressure, energy flow. All these things are not being described. So we need something which is called a stress tensor. Further, you will see the curvature of space-time, which is the complicated Riemann curvature tensor. That also cannot be defined by a 4 vector, and it is also not Lorentz transformation cannot be expressed. So all in all, what we can tell from here is that 4 vectors are essential. They are a very good mathematical tool, but cannot describe all the relativistic physics. So in order to understand, we need something which is called this. Okay, so we need the what are called tensors. And tensors are required, now you understand, because 4 vectors had a limitation. Now here is a quick, kind of a tabular understanding. What are the difference? So 4 vectors had 1 index, tensors are many index. This is used in flat space-time, that is used in curved space-time. This transform under Lorentz transformation, but as we will see in general relativity, we need coordinate transformation. This represents individual quantities and that represents across space-time. So this is a kind of a quick understanding of 4 vectors. Now, what you see from here is that this is what is called that the momentum 4 vector that gets actually generalized what is called a stress energy momentum tensor. So stress energy momentum tensor, again, because 4 vectors cannot define this, so you get what is called a stress energy momentum tensor. Now here you can see that there are diagonal elements. I have highlighted those in red. T11, T22, T33. So these are just normal stress. When we talk of a stress in general in stress mechanics, etc., this is normal stress. The off-diagonal component, that is T12, T13, T23, they describe shear stress, which describes how different layers of medium slide past each other. Okay, so this is what is the stress energy momentum tensor. And now you can see that this stress energy momentum tensor is also featuring in Einstein's field equation, G mu nu, and you can see I have rounded this one, T mu nu. This is actually the source. So what it means that the left hand side of the Einstein's equation talks about the curvature part. And what is causing the curvature? That is the stress tensor, T mu nu. And you can now imagine that this T mu nu is coming from where? That is the original 4 tensor or the 4 vector. Now, because it is now generalized into in tensor, we get something like this. So isn't it wonderful? Isn't it beautiful? The transition actually teaches us a wonderful way of understanding mechanics and how it get there. So here is something you can see the bigger way. So what it tells is that the stress energy momentum tensor is a rank 2 tensor that describes energy, stress, etc. in a kind of a tensor form, matrix form, because it becomes easy for the equations to happen. Okay, now you see that what I would like to show you that it is not only stress tensor which get generalized. There is another thing which is called a position vector. Position vector is simple. It is just the position in case of Newtonian mechanics. But here you can see that this position vector also gets stretched, or I would say it also gets generalized. Okay, and this generalization happens. You can see F equals to ma can now be written as this one. Now, I'm not going to derive this, but you can see that F is the 3 force, m is the mass, and a is the acceleration. Now, what happens in 4 force? The classical force gets generalized, and P mu is the 4 momentum, and the 4 force takes this form, and the components of the 4 force are defined over there. So everything is getting generalized. Okay, stress tensor is getting generalized, force is getting generalized. And here you can see that in relativity, space and time unified. So for velocity, which we talk of Newtonian velocity, that is also generalized in a 4 velocity form. So what you can tell from here that 4 force, 4 velocity, 4 momentum, ordinary vectors, all of them are getting generalized in special relativity, because special relativity is flat space-time. It is in inertial frame of reference, and from there we get in general relativity, which is due to the curvature. So you really don't need to go through this mathematical part. I have just told you that why it is featuring over here. So you can see from here that the geodesic equation, which we will explore now, is also coming from the 4 force. So geodesic equation is basically the equations of motion. And you will be surprised if I tell you that geodesic equation, this one, d square x mu upon d tau square plus Christoffel symbol, etc., they also actually represents Newton's laws of motion. So ultimately, everything comes down to classical physics. But because of the problems in space-time, curvature, etc., we are changing those things. Okay. Special relativity also gives us a very wonderful thing which is called light cones. Now, I know that you have heard about light cones, etc. But before we go in light cones, we will first let us understand what is a space-time interval. Now, in general, what do we mean by interval? Interval is basically between 2 lines. We are calculating the distance. One line, we use this Pythagoras' theorem or the distance formula. And what we calculate is basically the what we call is the distance, simple distance. Here also we are doing this, okay? But as I told you that here we cannot use Pythagoras' theorem. Here we are using something which is called dx square plus dy square plus dz square. So overall, we can say that space-time interval is a way to measure distance between 2 events in space and time. But as you know, in space-time, moving forward in space and forward in time do not add up. Instead, what happens is that more movement in space makes the total interval smaller, and more movement in time makes the total interval larger. And that is what we call space-like interval, time-like interval. So understand that more movement in space makes the total interval smaller, and more movement in time makes the total interval larger. Okay, let me show you this wonderful diagram. You will understand. Here you can see what actually happens. So first concentrate on the yellow ones. The yellow ones. These are called light-like cones. Now, what do I mean if I state in a very simple language? Then what we say is that these are the paths that light rays or photons follow. Okay, since photons travel at the speed of light, so it always remain on the surface of the light cone. This is kind of a restriction. Okay, it remains in the light cone. So here you see ds square, which I told you, ds square is simple. You can think of the Pythagoras' theorem. It is equal to 0. Okay, that means it is null. Okay, since photons travel at the speed of light. Okay, now you concentrate on the blue ones. The blue one, you can see, these are basically what are called time-like geodesics. That means what they do is that they describe the motion of massive particles which move slower to the speed of light. For example, we human beings, we move slower to the speed of light. So this is what is called the interior, and you can see here that I cannot show you use the mouse pointer, but all the blue dots, they are staying within the line, within the cone. So these describe the motion of massive particles which stay inside the cone, which means it cannot exceed the speed of light. Clear? Then you see the red ones. These are called space-like geodesics, and this implies that they would move faster than the speed of light, which is not possible. So that is why it is called space-like. So I think it is now clear. Light-like means those which are moving close to the speed of light. Time-like means which are heavy particles, which are moving slower than the speed of light. And the light cone or the space-like are the red ones, which are moving, assumed to move closer than the speed of light, or more I would say, imply faster than the speed of light, which doesn't happen. And that is why they are saying on the outer part of the light cone. So this light cone actually gives us a very good understanding, and this is the concept of geodesic. Now, I would like to tell you that geodesic actually means measuring two lines, straight lines. Okay, so if you follow Newtonian mechanics, and if you take this bottle, it is a straight line. This is Newton's laws of Newtonian mechanics also have a geodesic. But in case of special relativity, these geodesics are straight lines. So you can see on the left hand side picture, all of them are basically straight lines. Okay, I just don't want to go in here. This is basically what is called the Minkowski metric, and it looks flat. Okay, so n00 equals to -1, etc. These all got meaning. Okay, so not n, I'm so sorry, it is eta 11, eta 22, eta 33. These are the spatial components, and they are positive. Okay, and all other entries are 0. All other entries are 0. This means there is no mixing between different coordinates. So eta 01, it is equal to eta 02, is equal to eta 03. So the time coordinate does not influence spatial coordinates directly. The different spatial coordinates do not mix with that, and this is why the Lorentz transformation only mix with one space direction but of time, but not all. So these are terms which apply to the spatial coordinate. And remember, this is Minkowski metric, so it is all flat. Now here is a quick note. Some books uses minus plus plus plus, and some books uses plus minus minus minus. Both of them are the same. I have mentioned this. Both of them are the same, but only it depends which convention you're using. So minus plus plus plus, it has got a space-time interval, and plus minus 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 also. Now the question is that we learned about all those things which are all good and fine in terms of a flat space-time. These are all flat space-time. As I told you, this looks like flat. But how it will look in a curved space-time? This is the final part of our today's discussion, and this is what is called space-time curvature and geodesic equation. And I will just have a glass of water because it's very hectic to. I hope you are all enjoying this. So space-time curvature and geodesic equation. Okay. Now, when I show you the geodesic equation, don't get afraid. It looks a little bit complicated, but it is not. Okay, first you see the first term d square x mu and d tau squared. Now, do you remember this is something which is equivalent to the formula of acceleration? If you remember the formula of acceleration in Newtonian mechanics, it is the same. That is second derivative of space and time, d square x by dt square. So that means it is the same thing which I was constantly telling, that it boils down to Newtonian mechanics, d square x mu. So x mu is the space-time coordinate and tau is the proper time. Proper time means the time which you see on your wristwatch. Okay, the gamma, mu, alpha, beta, these are Christoffel symbols. These are correction factors. I will tell you what it is. And now you see this entire one is the 4 velocity component. You remember I talked about 4 velocity, 4 momentum. So this is the 4 velocity component. So x mu means time, ct, and xyz, the 4 components. Now d square x mu and d tau square, as I told you, this is Newtonian acceleration. And when I say that this is equals to 0, it means that there is no curvature. But remember, here there is a curvature. In space-time curvature, there is a curvature, but still we are setting the geodesic equation to 0. Why it is so? Here is a catch. I will just tell you. So when I set any equation to 0, if I set Christoffel symbols to 0 in Newtonian mechanics or in special relativity, that means it is flat. It has got no curvature. But here I am saying that general relativity deals with curvature, but still I am setting this equation to 0. What is the magic? What is the problem? Okay, I will solve this magic out. But first, let me tell you this one. Here you can see that this one is basically the connection coefficient. Now, this is a little bit mathematical. I know you might not be enjoying this part of our discussion. I will discuss this a little bit later. But these are the Christoffel symbols. They are basically the connection coefficient. Now, what it tells, if I tell you what is that, then the Christoffel symbols actually describe how movement in one direction, alpha, if I take 2 directions, alpha and beta, then movement in one direction, alpha, how it is affecting the change in the another direction, beta. So you can think that the motion of a particle is affected by both the space-time coordinate and the direction which it moves. This is a very big difference with Newtonian mechanics. In Newtonian mechanics, you will see that the space-time coordinate is only affected, not the direction. But in general relativity, the direction is also affected. So here I would like to tell you is that because motion can be curved, acceleration at a point depends on both where the object is and which way it is moving. This is a very important thing. Again, I repeat, because motion can be curved, acceleration at a point depends on both where the object is and which way it is moving. So here you can see this alpha, beta. They do not represent the 2 velocities directly, but they determine how different coordinates affect motion. The 2 velocity terms appear naturally when we contract the Christoffel symbol. So alpha, you can think, could be a forward motion and beta can be a sidewise motion. Here I will like to tell you, for example, you are on a roller coaster. Okay, so your acceleration depends on where you are on the track and how fast you are moving in different directions. I'm sorry, this actually requires a discussion of differential geometry, but I won't do that. But just imagine that you are on a roller coaster, and here you can see that alpha and beta, these are the 2 directions. You can think alpha could be forward motion, beta could be sideways motion, and Christoffel symbol, that gamma factor, modifies acceleration based on both. So if the road is flat, for example, you just moves forward straight. If it is curved, your motion in one direction influences another. So the first velocity, you can see dx mu by d tau, it tells how we move in the alpha direction. And the second velocity, dx beta by d tau, it tells how we move in the beta direction. And the Christoffel symbol, this gamma, determines how these 2 velocities interact due to space-time curvature. I know it is a little bit complicated, but general relativity is a little bit complicated, and this is how it is. So the next part, it will make things easier. Now here you can see that the typical acceleration in Newtonian mechanics is depending only on position. Okay, and if I say in Poisson equation, etc., tomorrow we will discuss on this, it is the gravitational potential. So see the right hand side, the picture. So if I place a particle in a gravitational field, then what it does, its acceleration is fully determined only by the gravitational field at that location. So remember, in Newtonian gravity, acceleration does not depend on velocity of the particle. Does it? No. Do you take velocity into consideration when you're talking of acceleration? No. So if you place a particle at a certain point, its acceleration is only determined by the gravitational field of that location. So the gravitational force is the same whether you move up, down, left, or right. So that is why I tried to show, if you place a particle, whether you are moving up or left or down or right, it hardly makes any sense. The gravitational force is the same wherever you are, whether you are moving up, down, left, or right, only the position matters. And this is very important. In Newtonian physics, motion is affected by position, not by velocity, right? But gravity acts the same way in all objects, regardless how fast they are moving. But in case of general relativity, it does not happen. So here you can see what happens. If in general relativity, motion depends on both position as well as, I would say, in the direction. So if the object is moving radially towards or moving away, time dilation and gravitational acceleration can be strongest. And if an object is just moving tangentially, then for example an orbit, etc., spatial curvature affects different, leading to precision like perihelion precession of Mercury. So this is something which is a stark difference, very deep in understanding. So here it is a quick summary of what we have learned. So here you can see that velocity in Newtonian mechanics is how object affects through space and time. Okay, as you can see here, I have written V equal to delta x by delta t, which is the good old gravitational the acceleration. Okay, an object, for example, when it is moving in curved space-time, it is takes place of the Einstein field equation. Then we have got the Christoffel symbols, which is the correction factor, and then we have got this part, which is the dx alpha, which I told you, moving in alpha and beta direction. This is basically, it couples with different velocities, velocity components. Now, one thing I would like to tell you, whether you actually know it or not, remember that if we take Poisson equation, which we would be discussing tomorrow in the same time, so all these very difficult curvature and these equations, they actually turns down to F equals to ma. It actually turns down to Newton's laws of motion. I will say there is no difference as such. And that is why I told that this actually couples. Now, couples means not multiplying. Okay, this is also something you need to understand. Multiplication just means two numbers or terms are multiplied. Coupling means two things are connected. So when we say that the terms are coupled each other, space-time curvature couples different velocity components, it means the motion in one direction can influence the motion in another. So just in electromagnetism and electric field, electric field and magnetic fields are coupled. That means a changing in an electric field creates a magnetic field. In general relativity also, different velocity components are coupled because curvature makes motion in one direction affect the other. Okay, so here is a quick summary which I'm not going to read. You can just go through it. Space-time, Minkowski space-time, objects move in straight line. Then we go to geodesics. Then we follow this, and then finally the space-time itself is being curved. We got the Christoffel symbols, etc. Coming to the last part of our discussion, which is that why the geodesic equation. I told you that why the geodesic equation is set to 0. The answer is very simple. Geodesic equation is set to 0 means that the acceleration is entirely due to the curvature of space-time, and there is no additional force which is acting on the particle. Oh, okay, physics, very interesting topic. Thank you very much. Okay, now here we come to something which I want to say. That means, okay, let me give you an example. Say, for example, I have got this one. Can you see this? Okay, this is, for example, my I keep my specs over here. Okay, now say, for example, this part is curved. Okay, let me bring it a little bit closer. Now this part is curved. Okay, now here is a particle which slowly moves from here to here. Now it won't move in a straight line. If you see, the particle will start from here and it will go just like this. It will be curved. Okay, now here you are watching this, you will see, oh no, there is a force. Then how this particle is moving? If there is no force, for example, my fingertip, how it is moving? Definitely there is an acceleration. Definitely there is something which is moving. But the fact is that it is not. In general relativity, particles actually do not move due to a force. There is no force over here. It is just following the curvature of space-time. Now see this picture. This person who is watching the particle trajectory, I cannot show you the animation here. This red one which is moving over the sphere, okay, this person outside is finding there is a force. That is why the particle is moving. But the fact is that there is no force. The particle is actually following the path which the curvature of space-time is there. It arises naturally. I will just try to give you an example. I don't know whether you have heard of Professor Amol Kumar Roy Chaudhary, a famous person whose Roy Chaudhary equation was used by Roger Penrose and Stephen Hawking. So I remember in an interview when Amol sir was asked that, what is a geodesic? Give me, sir, a simple example. So I think it was College Street or Jadavpur University where he was standing, and there was a tram line which was there. So he asked one of the students that, can you tell that in which direction this tram will be going in Calcutta? So the person told that if you are given initial conditions, position and momentum, then obviously you can tell where the tram will be going. Now, Professor Roy Chaudhary told that this is where the difference is. The tram does not need any acceleration or any momentum, anything. It will just follow the path where the tram line is. So if it is this way or that way, it will just follow in that direction. So this is what is called the difference, that it is not actually, there is no force. Okay, that is why we said the geodesic equation is equal to 0. It is not that it is, there is no curvature. Curvature is there. Equal to 0 means there is no force. And the particle here, you can see, is following the straightest possible path. But because the curved sphere, it is called a positive curvature, a particle moving along a geodesic, for the outside person, it is coming as accelerating. But the fact is that there is no acceleration. There is no pushing, no force that makes the particle accelerate, and it follows the straightest possible path. And this is what is called a geodesic. Okay, this is a very interesting part. Here is a quick note that acceleration is just a consequence of the geometry of space-time itself. And the curved space-time actually tells where you will move. And this brings us to the end of our lecture today. Here you can see that this person who is falling, free fall is equal to no acceleration. So an object in free fall feels no force and moves along a geodesic. This means astronauts in orbit experience that weightlessness. So here you can see a person on Earth will always find g equals to 9.8 m per s square. But right? So, but this is just a coordinate effect. Here you see it is 9.8 meter per second square, but actually there is no acceleration. And that is why the geodesic equation is being set to 0. Okay, that is why the equation is set to 0. So that is why I have written that it describes free fall, and according to the equivalence principle, that is gravity and acceleration is the same, they are just moving along the space-time's natural path. And that is the reason it is set to 0. So I hope you understand that why the geodesic equation is set to 0, because there is no force. So finally, we will wrap up today's session with just few important points. So we learned what is called the birth of general relativity, the Entworth paper. We also learned that how it is united in a space-time. And once it is united in a space-time, we get something which is called a 4-vector that is required. Okay. Then we learned that how moving clocks run slow, and that is due to one and so speed and velocity, another is the gravitational time dilation, and we need tensors because 4 vectors cannot define all those things. Then we find out what is called the Minkowski space-time, which is on flat space. And then we found that velocity and motion in flat space-time and how it happens in curved space-time. And then we learned the most important thing. This is the big difference. Please don't forget, the Christoffel symbols are calculated from the metric tensor. Remember that the term involves the components of the particles for velocity. The most important difference from Newtonian gravity and Einstein gravity is that the gravitational force and hence acceleration in Newtonian gravity depends on the position of the particle and relative to the source of the gravitational field. But velocity is independent. We discussed earlier, the acceleration due to gravity in Newtonian physics is independent and has nothing to do with the particle's velocity. But the difference is that in general relativity, velocity plays a role in determining the motion of particles, whereas in Newtonian it does not. So we can say that in general relativity, the motion of a particle is influenced by both its position and velocity. And this is a fundamental departure from Newtonian gravity, where velocity has no impact on gravitational acceleration. And we learned about space-time interval. What is a geodesic equation is set to 0. Why? Because there is no external force which is happening over there. So that's all for today's session. Thank you very much. I know it has been long, but I just thought, just hold on for a second. I just thought that this is the best way to pay tribute to Albert Einstein, to give you an overview of general theory of relativity. I know it is not possible in one single session, but you see it is more than 1 hour. And I thank everybody for following this podcast today. Please subscribe to my other channel where I'm really working hard, General Relativity Explained, and where I'm trying to put up more videos on relativity. As you understand that every person learns from their mistakes. So when I started this channel 3 years back, I didn't have any idea of making videos, YouTube, etc. So on my new channel, I'm doing a much more, I would say, organized way, many more videos on relativity. I am putting more mathematics in that. You will find I will come up with vectors and tensors, complex analysis, electromagnetism. So this will be done step by step. So please support me on that channel also. Tomorrow, I will be back, same time, 8 o'clock. But it won't be relativity, but it will be very interesting. I will be talking on some of the very fundamental concepts of physics as a whole, overall physics. That would include relativity also. But we will touch base those concepts and we will learn from there. It will be round about an hour session. And I hope that you will also enjoy and you will join tomorrow. Same time, same channel, 8 o'clock. I will see you soon. Now, I will just wait that if you have any questions in 2-3 minutes time, you can just ask me, or any feedback. How do you like today's podcast? I will wait. Otherwise, we can sign it off. How was the session? Avinash, Physics RMR, Meet Shah. Any feedback you want to give, or I can just wrap it up? Any questions from your part on anything you would like to share or anything? Can we have a webinar on Python in relativity and cosmology? Well, I don't know really Python. You're talking of the programming language. I will try to find out a speaker, Dr. Rahman, who can speak on Python in relativity and cosmology. I think you're talking of the programming language Python, right? I don't have any idea. So I will try to find out, definitely. Okay, and yeah, that's it. Tomorrow I will be back on this channel, and on Sunday on my other channel there will be a podcast on singularity, black holes, and cosmology. So you can join in and you can ask your questions. So thank you very much for joining, and see you tomorrow. Take care. Goodbye.